On June 17, 1775, British troops attacked a small hill outside of Boston, which American soldiers had used to bombard the city. Throughout the afternoon they sent wave after wave of troops up against the American soldiers ensconced at the top of Bunker Hill, yet the Americans simply continued to pick off British troops as they came. Muskets were the weapon of choice for both the British and American forces. The most commonly used version was the Brown Bess, a musket popularized during the 7 Years' War. The musket was a relatively inaccurate instrument overall because it lacked a sight, smooth bore, and often had a particularly small capacity to hold ammunition. It was also extremely cumbersome because it could only shoot 2 or 3 rounds every minute. The Brown Bess generally had a range of about 100 yards for an experienced shooter. During combat, however, troops were generally placed only 50 yards from each other to increase accuracy. Shooting the enemy at close range was the only way to ensure success. During the battle, an unknown officer directed the American shooters not to fire on the upcoming British troops until they saw the whites of their eyes. The phrase was passed down and has since become ingrained in Revolutionary War lore. We decided to test why that officer would have chosen the whites of their eyes. How far away would a soldier have to be for an American to shoot him? Why would the officer have chosen the whites of their eyes as opposed to another facial feature? Regardless of why he chose it, the method he proposed certainly proved stunningly effective. The Americans eventually ended up inflicting a huge number of casualties on the British Army. The total casualties and deaths reached over 1,000. The battle was also devastating to the pool of British officers leading royal forces in North America. About 100 officers were injured or killed on Bunker Hill. That amounted to about a third of the British officers deployed at the time. Thus, although the Americans eventually surrendered the hill to the British, Bunker Hill became known as a Pyrrhic victory for the Americans. The battle proved to the world that an inexperienced band of American militiamen could take on the highly trained British Army.
To test the commander's decision to hold fire at Bunker Hill, we decided to test whether waiting until the enemy's eye whites are visible is a viable proxy for determining whether an enemy has reached the optimum range to open fire with the Brown Bess. First, we tested the null hypothesis that the mean maximum distance at which a person's eye whites are visible is equal to 50 yards, against the two-sided alternative hypothesis. After that, we wanted to test whether there is another facial feature or body part which could potentially be a better indicator that the enemy has entered the optimum firing range. The visibility of the mouth appeared to be a good estimate, so we tested the null hypothesis that the mean maximum distance at which a person's mouth is visible is equal to 50 yards versus the two-sided alternative hypothesis. We had 12 different Harvard undergraduates use a string to record the maximum distance of visibility of the eye whites and mouth of one 5'10" male student. In other words, they stood as far away from the male student as possible, given that they could still distinguish the whites of his eyes, and then a separate trial was done for the visibility of his mouth. They used a string and a yardstick for measurement, and we made sure that each student did not see the other student's measurements so as to maintain a level of independence in our observations. We looked at the summary statistics of our data to get a general sense of the consistency of the results and their relation to our hypotheses, and then we conducted the actual hypothesis tests on the means using the student t-distribution. We chose to conduct t-tests because we figured that it is reasonable to assume that the distances of visibility are normally distributed, but the true variances of the distances were not known. Our observations for eye whites and the mouth were relatively consistent with respective standard deviations of only 1.4 yards and 7.4 yards. Judging by the mean and median of each dataset, it appears that using eye whites visibility as a proxy for estimating a distance of 50 yards is not a good estimate at all. Instead, it indicates a distance just under 20 yards. On the other hand, glancing at the mouth distance data indicates that mouth visibility is actually a relatively good proxy for 50 yards. The histograms of each dataset highlight that the observations were relatively consistent, but the normal approximation of the distribution of distances for both datasets does not appear to be very accurate. However, this is most likely due to the small size of our observation pool. Both eye whites and mouth distance test statistics yield p-values less than 0.05. Therefore, we reject the null hypotheses that the mean maximum distances of visibility of eye whites and of the mouth are 50 yards. While both null hypotheses are rejected at an alpha level of 0.05, the results for eye whites and mouth recognition distance are very different. For eye whites, we see that the test statistic of negative 78.2 is much greater in absolute value than the absolute critical value of 2.2 for a two-sided t-test with 11 degrees of freedom. By looking at the 95% confidence interval, we can see that eye whites visibility is nowhere near 50 yards. On the other hand, the mouth distance test statistic of 3.28 is much closer to the critical value of 2.2. The p-value is still low enough, however, that we would reject the null hypothesis even at a 99% confidence level, but we can still see from the 95% confidence interval that using mouth visibility is actually a relatively good practical proxy for a rough estimate of 50 yards, as the bottom bound of that interval is 52.3.